Look at some examples out of section 5.5. So let's start out by reminding ourselves that if we need to take the derivative with respect to x of a to the u, that's very similar to the derivative of e to the u, which is your base to the power times the derivative of your exponent. The only difference here is that if the base is not e, we pick up a natural log of our base out front. You could use this rule for even e to the u, and when you take the derivative, it would be natural log of e times e to the u times the derivative of the exponent, but natural log of e is just 1. Base e, that's e, e to the first makes e, so that's just 1. So really, that's what we use when we take the derivative of e to the u. So let's work through this example. So our a is 3, our u is x, u prime with the derivative of x is just 1, so our derivative is just natural log of a times a to the u times u prime, or just natural log of 3 times 3 to the x. And that's all we have to do for that one. This one, if we want to take the derivative of this one thing we have to look at is that we have a quotient. We have something in the numerator that has a variable, so we have a function on top. We have something in the denominator that has a variable, so we have a function on bottom. So a fraction that's a function on top, function on bottom, we have to use the quotient rule, unless we rewrite this and put it in a different format so that we can use the product rule. But we'll just use the quotient rule. So if we take the derivative of the numerator, that's going to be natural log of the base times a to the u times the derivative of the exponent. Well, what's the derivative of 2t? That's just 2. So we could just call that 2 natural log 3 times 3 to the 2t. So that's the derivative of the numerator. If we take the derivative of the denominator, if the denominator is t, the derivative of that is just 1. So remember, the quotient rule is u prime times v minus u times v prime, all of that over v squared. Our derivative will be u prime 2 times natural log 3 times 3 to the 2t times v minus u, 3 to the 2t, times v prime, all of that over the denominator squared. The one thing we can do is both terms on top have a 3 to the 2t power. What do I mean by terms? Just a reminder is that if we have something minus something, each of those are terms. Terms means adding and subtracting, so we can factor out a common factor. Each of those have the 2t in them. So if we take a 3 to the 2t out of the first term, we're left with 2 natural log 3 times t. If we take 3 to the 2t out here, we're left with a minus 1, all of that over t squared. And then we can't reduce that anymore. That t is part of a term. We can't use that to reduce here. The only thing you could really do is you could move that 2 up to the exponent here and call that natural log of 3 squared or natural log of 9. But this is sufficient just like it is. All right, so let's go on to the next one. So here we have log base 5 of a square root. So what is the rule for taking that? When we had just natural log of u, the derivative of that with respect to x was u prime over u. So natural log has a base of e. This is still a logarithm, it just has a different base. So we should expect to have a similar derivative. The only difference is going to be our bases aren't the same. So how's that one going to work? Well, if we take the derivative of log base a of u, take the derivative of that with respect to x, then we're going to have u prime on top, u on bottom, and just like with natural log, but we're going to have a natural log of a on bottom, a being our base. So several ways we could write it. Sometimes you see it u prime over u times 1 over ln of a. Sometimes you see it written this way. One of the biggest things here is just to make sure when we have natural logs or logs times other things that it's clear what we're taking the log of and what we're not taking the log of. Here we are not taking the log of this part. We're taking the log of just a, and that result gets multiplied times u. So and by getting rid of the square root on this one. If we have the square root of a polynomial or whatever, we can rewrite that as to the 1/2 power. And one of the properties of logarithms says that if we have log of something that has an exponent, we can put that exponent in the front. And we can call that 1/2 log base 5 of simply 2x minus 3. So this 1/2 is a coefficient, so we leave it alone, and then we take the derivative of that part. So we have our u prime over u. So the derivative of u, that part is our u. The derivative of that is 2 over u times natural log of a. Well, what is a in this case? A is our base, so natural log of 5. Notice that this 2 here and that 2 there. If we simplify that, we're left with 1 over natural log of 5 times 2x minus 3. So that's our derivative of that log. So we go on to the next one. We have another log. So notice we have a quotient in here. And remember that when we have products, quotients, exponents, things like that, inside our logarithm, we can use properties to rewrite this. If we left it just like it is, then when we did u prime over u, if that whole thing is considered u, that derivative would be a little messy because we would have to use the quotient rule there. But if we use properties of our logarithms, before we take the derivative, we can make this a little simpler. So if we have a quotient on the inside, we can take log of the numerator, and we can take log of the denominator, and we subtract those. Whatever factor we have on top, that term is positive. The factor on bottom, that term is negative. We could, if we wanted to, bring this 2 out front, but the derivative of this is a fairly simple derivative. So if you want to, you can just leave it as it is. So now as we progress, we can take our derivative. So it's u prime. So for the first term, if that's u on bottom, u prime on top, so the derivative of x squared is 2x. And remember, we multiply the denominator by natural log of our base, which is 5. For the next term, u goes on bottom, the derivative of u goes on top, and that gets multiplied times natural log of our base. On the first term, this x will cancel one of those x's, so we can call that 2 over, and I like to, if I have something times a natural log, I like to put that in the front like this. That way there's no confusion on what am I taking a natural log of. So x is times the natural log of 5. For the second term, let's put the x minus 3 in the front so that we know it's times natural log of 5. Neither of those reduce anymore, so we can stop with it there. So the other problems in this section have dealt with derivatives. This one is dealing with integrals. So we have 2 terms. The first one is just x to a power. And remember, when we do an antiderivative, we're going in the opposite direction. So instead of bringing our exponent down and decreasing our exponent, we increase our exponent and divide by the exponent. When we have, when we integrate a to the x, that's related to the derivative of a to the x. when we take the derivative of a to the x, remember that's a to the x times x prime, or if that's a u, it's a to the u times u prime times natural log of the base. If we're doing an antiderivative, if we have this, so imagine we take the antiderivative of both sides. So let me rewrite that down here. The derivative of a to the u is natural log a times a to the u times u prime. So if we integrate both sides, the derivative and the integral undo each other. U prime essentially is du. So if we have a to the u du, we don't have this natural log a, so let's divide both sides by natural log a. Or we can put 1 over natural log a. So, long story short, if we're integrating a to the u du, we're integrating a to the u du, that equals a to the u times 1 over natural log a. Remember when we integrated e to the u du, that just was e to the u, and then plus c. Well, the integral of a to the u du is a to the u, but since we have a different base, instead of multiplying by ln of a, we divide by ln of a. Because it's not a derivative, it's an integral. It's the inverse, or the opposite. So, clear up that. So, you don't have to rewrite it, but you can rewrite it into two separate integrals. The integral of x to the 6 plus the integral of 7 to the negative x dx. So we integrate the first one, that's x to the 1 greater power over that power. When we integrate this one, that's a to the u. If u is negative x, du is the derivative of that, negative 1 dx. So we need this to be du. So we need to multiply by negative 1 there to make that du. And if we multiply by negative 1 there, we need to divide by negative 1 out front. So that we have 1 over negative 1, or minus 1, times the integral of a to the u du, a to the u du. And we said that that integrates into 1 over natural log of the base times a to the u plus c. So the integral of e to the u is e to the u. The integral of a to the u is a to the u times 1 over natural log of the base. So we can leave it like that, or if you would rather, you can simplify that a little bit. So one last problem in this section. This has to do with finding an area. So let's start out by sketching this area. So 5 to the x, that's an exponential. If x is 0, 5 to the 0 is 1. If x is 1, we get 5. If x is 2, we get 25. So we have something that's going up exponentially like that. Y equals 0 is the x-axis. X equals 0 is the y-axis. X equal 2 is here. So we're looking for this area in between here. So remember how we find the area of a region. We integrate the function that gives us those y values. So the height of that, those y values, are given by f of x. And then we want to integrate that from left to right. We go from an x value of 0 to an x value of 2. So this integral gives us the area from our function to the x-axis. Now in the future, we'll look at, well, what if we're not going to the x-axis? What if we go past the x-axis or don't make it all the way to the x-axis? How do we handle that then? But since we're going to y equals 0, we are going to the x-axis. We need our antiderivative. We don't want to do this as a Riemann sum or as a lot of rectangles. So if this is a and that's u, if u is x, then du is just 1 dx. So that is du. So we said that the integral of that, the integral of a to the u is a to the u times 1 over natural log of a. So in this case, we have 1 over natural log of 5 times 5 to the x. A to the u, a to the u, a to the u. We want to evaluate that from 0 to 2. So if we put a 2 in, some people prefer to, instead of write this as a product, they prefer to write it as a quotient. So you could call this 5 to the second over natural log of 5 instead of times 1 over natural log of 5. So that's when we put a 2 in. Then if we put a 0 in, then we have 5 to the 0 over natural log 5. 5 squared, that's 25 over natural log 5. 5 to the 0 is 1. We have the same denominators, so subtract the numerators. So that's the exact area of that region. So that's an overview of integrating a to the u's, taking the derivative of a to the u's, and dealing with logs of other bases other than natural log.